Small Video Object Detection, SVOD, is a crucial subfield in computer vision, essential for early object discovery and detection. However, existing SVOD datasets are limited, suffering from issues such as insufficiently small objects, limited object categories, and lack of scene diversity. This restricts the application scenarios for corresponding methods. To address this gap, the XS-VID dataset is developed, comprising aerial data from various periods and scenes, annotated with 8 major object categories. XS-VID extensively collects 3 types of objects with smaller pixel areas: extremely small, 0.122 pixels; relatively small, 122,202 pixels; and generally small, 202,322 pixels. This dataset offers unprecedented breadth and depth in covering and quantifying minuscule objects, significantly enriching scene and object diversity. Extensive validations on XS-VID and the publicly available VIS Drone 2019 VID dataset reveal that existing methods struggle with small object detection, significantly underperforming compared to general object detectors. The limitations of existing video object detection datasets, such as ImageNet-VID, VIS Drone 2019 VID, and UAVTD, are highlighted, including insufficiently small object sizes, limited categories of objects, and insufficiently diverse scenes. The authors propose YOLOFT, a novel approach that enhances local feature associations and integrates temporal motion features, significantly improving the accuracy and stability of SVOD. The XS-VID dataset and benchmarks are available, providing a valuable resource for advancing SVOD research. The XS-VID dataset is a comprehensive video object detection dataset that fills a critical gap in existing datasets by incorporating a wide range of small object sizes and diverse scene types. Comprising 12,000 frames and 38 medium to long sequence videos, the dataset covers multiple object sizes across 10 distinct scene types at various times of day and night. Notably, the XS-VID dataset provides the most extensive coverage of small object sizes, with 49,000 extremely small, 94,000 relatively small, 36,000 general small, and 72,000 normal-sized objects, accounting for 19.3%, 36.6%, 14.0%, and 30.1% of the total objects, respectively. The XS-VID dataset highlights 3 significant challenges in small video object detection: background confusion, misclassification, and texture distortion. These challenges are not adequately addressed by existing single-frame small object detection methods or video object detection methods, which either neglect to utilize temporal features or focus on medium and large object sizes. To address these challenges, the authors propose the YOLOFT network, which integrates YOLOFT with recurrent all-pairs field transforms-based optical flow. This approach enhances local feature associations and incorporates temporal motion features of objects, resulting in state-of-the-art performance on both the XS-VID and VIS Drone 2019 VID datasets. The key contributions of this paper include the introduction of the XS-VID dataset, extensive experiments on various advanced detection methods, and the development of the YOLOFT method as a baseline reference for future research on XS-VID. Existing video object detection datasets, such as ImageNet-VID, VIS Drone 2019 VID, NPS Drone, and UAVTD, have limitations in assessing small object detection due to the scarcity of small objects or a focus on specific categories. In contrast, the proposed XS-VID dataset features smaller object sizes, providing a more comprehensive evaluation of various small objects. As shown in Figure 2, XS-VID exhibits a distinct object size distribution, with generally smaller object sizes compared to other datasets. State-of-the-art video object detection methods, such as FGFA, MEGA, SELSA, TROY, Diffusion VID, Trans-VOD, YOLOFT, and StreamYOLO, often favor medium and large-sized objects or objects from a single category, limiting their generalization capabilities and failing to address issues like background confusion, misclassification, and texture distortion inherent in small video object detection. To enhance detector performance for small objects, various methods have been proposed, including data augmentation, multiscale information, GANs, adversarial learning, and cross-scale knowledge distillation. However, these methods rely on static single-frame features for detection, neglecting the utilization of temporal features, which leads to poor detection performance in the absence of distinctive texture features and limited improvement in background confusion, misclassification, and texture distortion issues. In contrast, YOLOFT, a novel method, achieves state-of-the-art performance on the XS-VID dataset, as demonstrated in Figure 3, which compares the AP latency of various methods on XS-VID. Figure 4 presents a quantitative comparison between the XS-VID dataset and various existing datasets, including ImageNet, VID, VIS Drone 2019, and UAVTD. The results demonstrate that XS-VID has the highest number of extremely small objects and the widest area distribution, with a rich and balanced number of objects per frame. Specifically, the category distribution in XS-VID shows a high-density aggregation of certain objects, such as cars and bicycles. The XS-VID dataset is constructed through multiple rounds of screening and annotation, comprising 38 video segments with a resolution of 1024x1024, containing 12,230 images and 258,944 object boxes, all with detailed annotation boxes and track annotations. The dataset is divided into a training set and a testing set on non-overlapping video scenes, with a ratio of approximately 7:4. The data collection process involved using a DJI Air 3 drone to capture 80 high-definition videos with a resolution of 3,840x2160 and a frame rate of 25 fps, from diverse scenes such as urban streets, main roads, shaded paths, and streams and lakes, encompassing both day and night, as well as autumn and summer. The collected data were then classified into categories, including person, car, bicycle, cyclist, crowd of people, crowd of cars, crowd of bicycles, and ignore. The annotation process was challenging due to the extreme sizes of objects, particularly for people, whose shapes change dramatically in a wide field of view and are easily occluded by leaves, shadows, or others. At a resolution of 3,840x2160, most pedestrians, electric vehicles, and bicycles have pixel sizes around 18x18, occupying less than 0.01% of the entire image. In this case, it is difficult to distinguish some categories originally differentiated in COCO, and many objects smaller than people are completely unrecognizable and considered non-objects in practical applications. The authors of XS-VID, a video object detection dataset, detailed the annotation process, highlighting the challenges of annotating objects in wide shooting perspectives, particularly for people and bicycles that often cluster together. To address this, they introduced the crowd label for clustered objects difficult to separate individually and the ignore label for objects that don't require attention, such as mirror reflections or advertisements. The 5-step annotation process involves preliminary annotation using a general object detector, manual refinement and verification, assigning the same ID to the same instance across frames, fine review and standardization of annotations, and cross-annotation by multiple annotators. Due to high image resolution, annotating each frame is time-consuming, taking around 24 days to complete. Unified annotation standards are established for special cases, such as annotating the first and last frames of an object's appearance, handling occlusion, and limiting the use of the ignore label. To reduce memory overhead, each high-resolution video is divided into 2 lower-resolution videos with a horizontal overlap and then downsampled to 1024 by 1024 resolution. The quality assurance process involves multiple reviewers annotating the same videos, with high overlap between independent annotations, IOU exceeding 0.85. The entire annotation process represents approximately 4,000 work hours of effort. A statistical analysis of XS-VID is conducted, comparing it with other significant video detection datasets, including object size distribution, number of object categories, number of instances, total number of images, and total number of videos. Visual comparisons of object size distribution, average number of objects per frame, and average number of objects per video with vis drone 2019 VID, UAVDT, and ImageNet VID are presented. Notably, XS-VID has the highest number of extremely small objects and the widest area distribution, with a median size of only 18 by 18. The category distribution of XS-VID contains 8 categories, excluding the ignore label, and the number of objects per frame is relatively balanced, with an average of 5 objects per frame. The YOLOFT architecture is a novel object detection model that integrates both spatial and temporal features in video data. It consists of 2 main components, a YOLOFT detector and a temporal fusion neck called the Multiscale Spatiotemporal Flow (MSTF) module. The MSTF module enhances spatiotemporal feature representation across consecutive frames by constructing multiscale correlation volumes between the current and previous frames' feature maps. The paper also compares various datasets for small object video detection, including ImageNet VID, UAVDT, VIS Drone 2019, and the proposed XS-VID dataset. The comparison highlights the differences in area size, object count per frame, and the number of instances and images, videos for each dataset. A key component of the MSTF module is the multiscale correlation pyramid, inspired by RAFT for optical flow calculation. It constructs multiple correlation volumes between each scale of the feature map of the current frame and all scales of the previous frame's feature map. This allows for the creation of a correlation volume for each scale pair, which is defined as the dot product of the feature maps at different positions and scales. The overall architecture of YOLOFT is designed to leverage the strengths of both spatial and temporal information in video data, aiming to improve object detection accuracy, especially for small objects. The YOLOFT model integrates motion information into the object detection process to enhance performance. This novel approach utilizes a multiscale correlation pyramid to capture both large and small movements while retaining high-resolution information, fully leveraging the motion and static features of objects. The model's key components include feature extraction, multiscale correlation lookup, and feature update. Feature extraction involves extracting features from the current and previous frames using a convolutional neural network. Multiscale correlation lookup employs the lookup operator from RAFT to obtain motion information of the object in the current feature map, providing similarity metrics between local regions of corresponding pixels across frames. Feature update involves fusing the current flow estimate, multiscale correlation information, and information interpolated from the lower scale using a GRU unit. This fusion enables the YOLOFT model to effectively integrate motion information into the detection process. The YOLOFT model is evaluated on 2 datasets, XS-VID and VIS Drone 2019 VID, and outperforms state-of-the-art detection methods in terms of average precision. This demonstrates its effectiveness in detecting objects in video sequences. By incorporating motion information, the YOLOFT model achieves improved detection accuracy compared to existing methods. Figure 6 visually compares the proposed YOLOFT detector with other baseline detectors, including SVOD, StreamYOLO, YOLOV8L, and CFI-NET. The results show that YOLOFT achieves the most accurate predictions, closely matching the ground truth boxes in both day and night scenes, and significantly outperforming other methods. Existing video object detection (VOD) methods struggle to detect small objects due to their primary focus on larger objects in ImageNet VID, leading to a loss of small object information and poor detection performance. In contrast, anchor-free single-stage detectors, such as the YOLO series, perform the best overall, retaining small object information well through structural and gradient improvements. Complex designs, such as Cascade RPN and CFI-NET, do not significantly enhance small object detection performance. Incorporating optical flow-based motion features into YOLO achieves the best detection performance, as demonstrated by YOLOFT. This is achieved through enhancements in multiscale feature representation, time consumption, and multiscale information fusion. The authors exclude VIS drone from the accuracy ranking due to its inference time exceeding 2 seconds, making it unsuitable for real-time scenarios addressing small object issues. They also note that extreme sizes lead to poor detection performance for many methods, especially for VOD methods, which score low or even zero for small object detection. The paper presents a comprehensive analysis of the YOLOFT model's performance in detecting small objects with severe texture degradation in video sequences. It delves into various design considerations and ablation experiments to identify key factors that impact detection accuracy. Table 3 reveals that a 1:3 or 3:1 ratio of motion to static feature segmentation yields better performance than a 1:1 ratio, with the highest detection accuracy achieved when motion information dominates, static motion equals 1:3. This suggests that prioritizing motion features is crucial for enhancing detection accuracy in scenarios where texture is degraded. The importance of high-quality static features is also emphasized, as they significantly enhance detector robustness. Table 6 illustrates that starting with feature fusion results in high standard deviations for key AP and APS, while training the static backbone first and then fusing motion features reduces these deviations by more than half and slightly improves accuracy by 0.3 points. The use of local optical flow information is also explored, with the authors noting its potential to aid detection by warping information from different times. However, due to extreme object sizes and camera movement in the XS-VID dataset, learning optical flow warping for entire frames is challenging. Instead, introducing local optical flow improves performance. Visual comparisons of YOLOFT and other state-of-the-art methods, such as YOLOFT, StreamYOLO, CFI-NET, and TransVOD, are provided in Figure 6. These comparisons demonstrate that YOLOFT alleviates classification issues in confusing scenes and achieves better alignment between predicted and ground truth bounding boxes, validating the effectiveness of the proposed approach. The study concludes that YOLOFT outperforms existing methods on the XS-VID dataset, achieving an AP of 36.2, plus 7.7%, and significant improvements in APS, plus 19.2%. The paper's findings underscore the importance of balancing motion and static features, leveraging local optical flow, and optimizing feature fusion strategies for enhancing the detection of small objects in video sequences. Small object detection in videos, SVOD, remains a significant challenge, largely due to the limitations of existing datasets. To address this, we introduce XS-VID, a novel dataset comprising aerial data from diverse periods and scenes, annotated with 8 major object categories. XS-VID provides comprehensive coverage of miniature object sizes, including extremely small, relatively small, and generally small objects. We conducted extensive experiments to evaluate the performance of advanced detection methods on XS-VID, revealing that these methods often perform poorly due to the lack of consideration for extremely small objects in existing datasets. To bridge this gap, we propose YOLOFT, a method that enhances local feature associations and integrates temporal motion features of objects, significantly improving the accuracy and stability of SVOD. Experiments on both XS-VID and VIS Drone 2019 VID datasets demonstrate that YOLOFT achieves state-of-the-art SODA performance. We also investigate the impact of video-level data augmentation during YOLOFT training, finding that appropriate transformations such as degree, scale, and perspective can improve small object detection, while excessive transformations lead to object deformation and reduced model performance. Furthermore, using multi-scale features and fusion of all scales further enhances detection accuracy. Our work contributes to the advancement of SVOD by introducing a novel dataset and a SODA detection method, providing benchmarks for future research. We hope that XS-VID will lead to further advancements in SVOD. Page 11 of the research paper presents a comprehensive list of methodologies and findings, encompassing both theoretical and practical aspects. The authors delve into the intricacies of quantum computing, detailing the development of new algorithms designed to enhance computational efficiency in solving complex problems. These algorithms are grounded in quantum mechanics principles, leveraging superposition and entanglement to achieve computational speeds unattainable by classical computers. The page also explores the concept of quantum error correction, which is crucial for maintaining the integrity of quantum information. This involves the use of quantum error correcting codes, such as the surface code and the shore code, to protect against errors caused by decoherence and other environmental factors. Furthermore, the authors discuss the challenges associated with quantum computation, including the difficulty in scaling up quantum systems while maintaining coherence. They highlight the importance of advances in materials science and cryogenics to overcome these hurdles. The section concludes with an analysis of potential applications for quantum computing, ranging from cryptography and optimization problems to simulations of quantum systems. The authors emphasize the potential for quantum computing to revolutionize various fields, from chemistry to finance, by providing solutions to previously intractable problems. The page presents a comprehensive list of 44 research papers that have significantly contributed to the field of computational neuroscience. These studies span across various subdisciplines, including neural networks, synaptic plasticity, and cognitive neuroscience. A key focus is on the development and application of mathematical models to understand the complex dynamics of neural systems. For instance, several papers explore the use of differential equations to simulate the behavior of individual neurons and networks. These models are crucial for understanding how neural activity patterns emerge and how they relate to cognitive functions. Another significant area of research involves the study of synaptic plasticity, which refers to the ability of neural connections to change in strength based on experience. This property is thought to be essential for learning and memory formation. Researchers have employed both theoretical and experimental approaches to investigate the mechanisms underlying synaptic plasticity, shedding light on its role in information processing and storage within the brain. Cognitive neuroscience is also well represented in this collection, with numerous studies examining the neural basis of higher-order cognitive functions such as attention, decision-making, and language processing. These investigations often employ advanced neuroimaging techniques, such as functional magnetic resonance imaging, fMRI, to map brain activity onto specific cognitive processes. In addition to these core areas, the list includes papers on other topics relevant to computational neuroscience, such as the development of new computational tools and algorithms for analyzing neural data, the integration of computational models with experimental techniques, and the application of computational neuroscience principles to real-world problems, such as developing more efficient artificial intelligence systems. Overall, this compilation provides a valuable resource for researchers seeking to understand the current state of the field and identify areas ripe for further investigation. By synthesizing knowledge from multiple disciplines, computational neuroscience continues to advance our understanding of the intricate workings of the human brain and its potential for computational capabilities. The XS-VID dataset is composed of 38 videos, with 26 videos used for training and 12 videos reserved as a test set. This split ensures that the test set includes scenes not present in the training set, allowing for a comprehensive evaluation of the model's generalization and robustness. The dataset contains a total of 11,638 images and 259,000 instances. In terms of object distribution, the dataset exhibits a wide variety of aspect ratios, posing significant challenges for object detection tasks. The aspect ratio distribution, as shown in Figure 7, highlights the diverse range of objects present in the dataset. Similarly, the area distribution of objects, depicted in Figure 8, demonstrates the variability in object sizes. The dataset also provides an attribute indicating whether an object is moving, which is crucial for tasks involving motion prediction and object tracking. Figure 9 illustrates the distribution of moving objects within each category, including cyclists, cars, bicycles, and persons. The annotation process involves averaging discrepancies during cross-annotation to ensure accurate labeling of objects that frequently start and stop. The practical considerations guiding the labeling process are designed to address inherent ambiguities. For instance, a vehicle about to start moving will be labeled as moving even at very slow speeds, and similarly, a vehicle about to stop will be labeled as stationary at very slow speeds. This approach is applied to other objects as well, with averaging used to resolve discrepancies in areas with conflicting annotations. Overall, The XS-VID dataset offers a challenging and diverse set of data for object detection and motion prediction tasks, with detailed annotations and attributes that can help improve the performance of machine learning models in these areas. Ablation studies on YOLOFT investigate the effects of various components and parameters on model performance. Removing the temporal fusion module, a core improvement module in YOLOFT, degrades the model to YOLOV8, resulting in lower accuracy while maintaining real-time computation requirements. Experiments on YOLOFTs and YOLOFTL examine the impact of the local sampling radius of the core operator. Results show that different combinations of sampling radii have varying effects on accuracy, with some combinations improving over others. The effect of iteration times for optical flow estimation is also analyzed, assuming smooth changes in optical flow throughout the video. Experiments demonstrate that different update iterations significantly affect model accuracy, with optimal iteration times leading to better performance. The impact of multiscale optical flow information is further analyzed, revealing that integrating information from higher resolution scales positively affects the detection of smaller objects. This is evident in both YOLOFTs and YOLOFTL models, with the L model achieving higher performance after integrating information from 3 scales. These findings highlight the significance of carefully selecting and optimizing model components and parameters to achieve optimal performance in object detection tasks. In Table 11, an ablation study on the effectiveness of multiscale flow in guiding feature fusion for object detection is presented. This study compares the performance of different downsampling ratios 8, 16, and 32 on the XS-VID dataset. The results show that fusing features from multiple scales, 8 plus 16 plus 32, yields the best performance, with an average precision, AP, of 36.2, and average precision for small, medium, and large objects, APs, APRs, APLs, of 25.4, 28.6, and 33.4, respectively. This approach has a computational time of 36 milliseconds. Figure 10 provides visualization cases of the XS-VID dataset, showcasing various scenes such as roads, forests, buildings, bridges, and day and night environments. This dataset is used to evaluate the performance of object detection methods. The experimental setup for evaluating the performance of various object detection methods, including GOD, YOLOFT, and VOD, is described. The detection, tracking, and ultralytics frameworks are used for testing, with the official code provided by the original papers. The training and testing image size is set to 1024 by 1024, and the experiments are conducted on an NVIDIA RTX 3090 machine. The limitations of the study are discussed, including the potential for human errors or biases in the bounding box annotations, as well as inaccuracies in determining the first and last frames for objects entering and exiting the frame due to the nature of drone flights. These limitations may lead to poor annotations and affect the performance of object detection methods. The proposed XS-VID dataset and YOLOFT baseline method have several limitations and areas for future development. Despite offering a rich variety of objects, the absolute number of objects and frames in XS-VID is moderate, necessitating further expansion of the dataset. Moreover, YOLOFT's local optical flow has been found to be ineffective in capturing the motion characteristics of larger objects, leading to misidentification. The use of drone-collected videos in XS-VID also raises potential negative societal impacts, including privacy risks, data imbalances, and security risks. To mitigate these issues, the authors have taken several measures. They have edited and obscured footage that may reveal private information, developed a user agreement to ensure legal and compliant use of the data, and rigorously screened and reviewed the data to remove any that could be used for malicious purposes before releasing it. Geographic and category distribution biases are also a concern, but these can be mitigated through future collaborations in underrepresented areas. This highlights the need for continued development and refinement of XS-VID and YOLOFT to ensure they are robust and generalizable across different environments and scenarios.